Running electrical generators on water alone. After many decades of being lied to, most people believe that it is necessary to burn a fuel, typically, a fossil fuel such as petrol or diesel, in order to make an engine run. Scientific experts demonstrate their ignorance by proclaiming that their calculations show that there is just not enough energy in hydrogen released through electrolysis, to provide enough power to run an engine which can provide sufficient electrical energy to perform the electrolysis in the first place. Their calculations are completely wrong as they are based on a major level of ignorance of the real facts. They are not aware that properly made HHO has typically 4 times the energy content of hydrogen gas. They are not aware that a properly built electrolyzer running on DC has more than double the efficiency that Faraday considered to be the maximum possible production rate of HHO for any given current flow. They are not aware that resonant pulsed electrolysis has several times the water to HHO conversion efficiency that straight DC can produce, resulting in more than 10 times the Faraday maximum conversion rate. They are not aware that the majority of the energy produced by HHO being converted back into water does not come from the hydrogen but instead comes from charged water clusters. It is likely that they have never even heard of charged water clusters. They are probably not aware that introducing cold water mist to the air entering an internal combustion engine makes that engine operate as an internal combustion steam engine as the mist gets converted into flash steam, raising the pressure inside the cylinder and boosting the engine efficiency very considerably. Because of these things, the calculations of the scientific experts produce completely wrong results due to lack of knowledge and the flawed assumptions on which the calculations are based. Interestingly, quite apart from the fact that generators running on water as the only visible fuel, have been powering off-grid locations 24 hours 7 days a week for many years now, and ignoring that little detail, check out this newspaper comment. U.S. Navy will turn seawater into fuel. The U.S. Navy claims it has found a way to turn seawater into fuel, having spent decades conducting scientific experiments. If true, the development could see military ships developing their own fuel and staying operational 100% of the time. Navy scientists say they have already used the new fuel to fly a model aircraft. Calling it a huge milestone, Vice Admiral Philip Cullum pointed out that in the Navy, we have some pretty unusual kinds of challenges. One of these is the need at present to refuel from an oil tanker. But developing a game-changing technology like seawater to fuel reinvents a lot of the way we can do business when you think about logistics readiness, said Cullum. The U.S. Navy has 289 vessels and most rely on oil-based fuel, apart from some aircraft carriers and 72 submarines that use nuclear power. The breakthrough came after scientists found a way to extract carbon dioxide and hydrogen gas from seawater. The gases are then turned into a fuel with the help of catalytic converters. We are in challenging times where we have to think in new ways to look at how we create energy, how we value energy and how we consume it, said Cullum. We need to challenge the assumptions that of the last 6 decades of constant access to cheap, unlimited amounts of fuel. This is a very interesting comment from Vice Admiral Cullum. Firstly, he confirms that the Navy's massive engines can be powered by gas produced by electrolysis. Second, he implies very strongly that refueling with oil-based consumables is no longer needed, and that means that the electrolysis is well in excess of 100% efficient, making those massive engines self-powered. Third, it seems reasonable to presume that if those massive engines can be self-powered through electrolysis, that the very much smaller engines in cars could also be run on electrolysis, even if the same method of electrolysis were not used. Anyway, we have to deal with the tiny, very inefficient motors which are used in generators which normally use petrol as the fuel. In the UK, 3 men managed to run a generator on water alone, using just simple things which are within the scope of the average handyman in his workshop. They bought a standard petrol-driven electrical generator off eBay and managed to run it without using any petrol. They used a HHO gas flow which they measured at just 3 liters per minute, and they test-loaded the 5.5 kilowatt generator with 4 kilowatts of equipment. Afterwards they abandoned the generator and moved on to a much bigger engine, as their plans are to sell electricity to the local power company. Their representative said, "The equipment was put together by my associate, who supplied the water electrolyte, not a standard electrolyte, 0.4% by volume. It was a 5 kilowatt petrol generator, about 300 cubic centimeters. We attached a Chevrolet alternator which constantly charges a 12-volt 55-amp-hour battery, which in turn powers 6 HHO tubes, each of which draws 6 watts, for a total of 30 watts. The outputs of these electrolyzers are connected in series and they feed the gas into a low-pressure butane gas camping tank which has an 18 psi pressure release valve. This tank feeds the air intake of the generator, which is adjustable with a choke. We loaded the 30-amp socket of the generator with various drills, heaters etc. working, for more than 4 hours. The maximum load which we tried was 4 kilowatts, being a bar heater, a kettle and 2 drills. The electrolyzer tubes are heavy-duty plastic, rated for 80 psi pressure. Inside are 4 tubes of stainless steel, 3 positive and 1 negative. Each tube created 1 liter of gas every 2 minutes, which is a total of 3 liters per minute. They eventually become warm to the touch, but they do not get hot. Running an electrical generator without fossil fuel. In broad outline. In order to achieve this objective, very much like Stan Meyer, we need to feed the engine 3 things. Air, this is fed in as normal through the existing air filter. HHO gas, how to make this has already been explained in considerable detail. A mist of very small water droplets, sometimes called cold water fog. Also, we need to make 2 adjustments to the engine. The spark timing needs to be retarded by about 11 degrees. If there is a waste spark, then that needs to be eliminated. To summarize then, a good deal of work needs to be done to achieve this effect. An electrolyzer needs to be built or bought, although the required gas production rate is not particularly high. A generator of cold water fog needs to be made or bought. Pipes need to be installed to carry these 2 items into the engine. The engine timing needs to be retarded. Any waste spark needs to be suppressed. Water tanks are needed for the cold water fog and to keep the electrolyzer topped up. Ideally, some form of automatic water refill for these water tanks should be provided so that the generator can run for long periods unattended. If we omit the electrical safety equipment which has already been explained in detail, and omit the HHO gas safety equipment which has already been explained in detail, and skip the automated water supply details and the starting battery, then, a generalized sketch of the overall arrangement looks like this. Here, they have opted to feed the HHO gas into the air system after the air filter, a thing which we normally avoid as it is not helpful for the HHO gas production efficiency, but the first step is to reproduce their successful method. Exactly before seeing if it can be improved further. Also fed into this same area is the cold water fog, which is comprised of a very large number of very tiny droplets. The air enters this area as normal, through the existing air filter. This gives us the 3 necessary components for running the generator engine without using any fossil fuel. Creating the cold water fog. There are 3 different ways to generate the spray of very fine water droplets, which are a key feature of the success of this way of running the engine. One way is to use a Venturi tube, which, while it sounds like an impressive device, is actually very simple in construction. It is just a pipe which tapers to a point and which has a very small nozzle. As the engine draws in the air HHO mix on its intake stroke, the mixture rushes past the nozzle of the Venturi tube. This creates an area of lower pressure outside the nozzle and causes water to exit through the nozzle in a spray of very fine droplets. Some perfume spray bottles use this method as it is both cheap and effective. An alternative method of making the cold water fog is to use 1 or more pond foggers. These are small ultrasonic devices which are maintained at the optimum operating depth in the water by a float. They produce large amounts of cold water fog which can be fed into the engine like this. A third method is to use a small carburetor of the type used with model aircraft. This does the same job as a regular engine carburetor, feeding a spray of tiny water droplets into the engine air intake. The physical arrangement of this option depends on the construction of the air filter of the generator being modified. You will notice that the people in the UK who did this, used a small gas tank with an 18 pounds per square inch pressure release valve. This is not possible with the highest quality of HHO gas as it cannot be compressed that much. However, with a lower grade of HHO which has some water vapor mixed in with it, it is possible to have a gas reservoir with that sort of pressure in it. In this case, except possibly for starting, their gas production rate is probably not high enough to allow much raised pressure inside the tank. Obviously, the gas pressure switch on. The electrolyzer and the one on the gas storage tank will have similar operational pressures. Some safety features. Up to this point, the electrolyzer has been shown in bare outline. In practice, it is essential that some safety features are incorporated as shown here. These safety devices should be familiar to you by now as they have already been explained earlier in this document. The reason for changing the timing. The fuels used with most internal combustion engines are either petrol, gasoline, or diesel. If you are not interested in chemistry, then you are probably not aware of the structure of these fuels. These fuels are called hydrocarbons because they are composed of hydrogen and carbon. Carbon has 4 bonds and so a carbon atom can link to 4 other atoms to form a molecule. Petrol is a long chain molecule with anything from 7 to 9 carbon atoms in a chain. Diesel has the same structure but with 11 to 18 carbon atoms in a chain. In a petrol engine, a fine spray of petrol is fed into each cylinder during the intake stroke. Ideally, the fuel should be in vapor form, but this is not popular with the oil companies because doing that can give vehicle performances in the 100 to 300 miles per gallon range and that would cut the profits from oil sales. The petrol in the cylinder is compressed during the compression stroke and that reduces its volume and raises its temperature substantially. The air-fuel mix is then hit with a powerful spark and that provides enough energy to start a chemical reaction between the fuel and the air. Because the hydrocarbon chain is such a large molecule, it takes a moment for that chain to break up before the individual atoms combine with the oxygen in the air. The main engine power is produced by the hydrogen atoms combining with oxygen, as that reaction produces a large amount of heat. The carbon atoms are not particularly helpful, forming carbon deposits inside the engine, not to mention some carbon monoxide, CO, and some carbon dioxide, CO2, as well. The key factor here is the slight delay between the spark and the combustion of the fuel. The combustion needs to happen a few degrees after top dead center when the piston is about to start its downward movement in the power stroke. Because of the delay caused by the hydrocarbon chain breaking down, the spark occurs a few degrees before top dead center. If you were to replace the petrol vapor with HHO gas, then there would be a major problem. This is because HHO gas has very small molecule sizes which do not need any kind of breaking down and which burn instantly. The result would be an explosion which occurs far too soon and which opposes the movement of the rising piston as shown here. The forces imposed on the piston's connecting rod would be so high that it would be quite liable to break and cause additional engine damage. In the case of our electrical generator, we will not be feeding it a mix of air and HHO gas, but instead, a mix of air, HHO gas and cold water fog. This delays the combustion of the HHO gas by a small amount, but it is still important to have the spark occur after top dead center, so the ignition of the generator needs to be retarded by 11 degrees. Engine design varies considerably in ways which are not obvious to a quick glance at the engine. The timing of the valves is a big factor here. In the smallest and cheapest engines, the engine design is simplified by not having the spark timing taken off the camshaft. Instead, production costs are cut by taking the spark timing off the output shaft. This produces a spark on every revolution of the engine. But, if it is a 4-stroke engine, the spark should only occur on the power stroke, which is every second revolution of the output shaft. If the fuel is petrol, then this does not matter as the extra spark will occur near the end of the exhaust stroke when only burnt gases are present in the cylinder. Some people are concerned when they think of HHO gas burning and producing water inside the engine. They think of hydrogen embrittlement and rusting. However, because of the nature of the hydrocarbon fuel already being used, the engine runs primarily on hydrogen anyway, and it always has produced water. The water is in the form of very hot vapor or steam, and the engine heat dries it out when the engine is stopped. Hydrogen embrittlement does not occur as a result of using a HHO gas booster. Anyway, if we were to delay the spark until after top dead center as we must, then the situation is quite different, as the waste spark will also be delayed by the same amount. With most engines, at this point in time the exhaust valve will have closed and the intake valve opened. Our very flammable gas mix will be being fed into the engine on its intake stroke. This means that our gas supply system is openly connected to the cylinder through the open intake valve, and so, the waste spark would ignite our gas supply system, as far as the bubbler, which would smother the flashback. The situation is shown here. We definitely do not want that to happen, so it is very important that we suppress that additional waste spark. So, this leaves us with two engine adjustments: timing delay and waste spark elimination. There are various ways in which these can be done, and as each engine design is different, it is difficult to cover every possibility. However, there is a technique which can be used with many engines and which deals with both issues at the same time. Most engines of this type are four-stroke engines with intake and exhaust valves, perhaps something like this. The intake valve, shown on the right in this illustration, is pushed down by a camshaft, compressing the spring and opening the inlet port. The exact arrangement will be different from one engine design to the next. What is fixed is the movement of the valve itself, and that movement only takes place every second revolution. There are various ways of using those movement to eliminate the waste spark and retard the timing. If a switch were mounted so that it opens when the intake valve opens and closes when the intake valve closes, then the switch closure shows when the piston starts upwards on its compression stroke, and a simple electronic circuit can then give an adjustable delay before firing the coil which produces the spark. This, of course, involves disconnecting the original electrical circuit so that no waste spark is generated. The current flowing through the switch contacts can be arranged to be so low that there will be no sparking at the contacts when the circuit is broken again. The switch positioning might be like this. An alternative is to attach a strong permanent magnet to the rocker arm, using epoxy resin, and then position a solid-state Hall effect sensor so that it triggers the delay before the spark is generated. If the engine did not have a waste spark, then in theory, the timing mechanism of the engine could be used to retard the spark. However, in practice, the timing mechanism is almost never capable of retarding the spark to the position that is needed for running without fossil fuel, and so, some kind of delay circuit will be needed anyway. The sort of delay circuit needed is called a monostable, as it has only one stable state. A basic circuit of that type is. If you are not at all familiar with electronic circuits, then take a look at the beginner's electronics tutorial found in the chapter 12.pdf document on the http://www.freeenergyinfo.co.uk website, as that explains how circuitry works and how to build any simple circuit from scratch. We can use two of these circuits, the first to give the adjustable delay and the second to give a brief pulse to the ignition circuit to generate the spark. Making the HHO gas. When the generator is running, we have a ready supply of electrical energy, coming from a piece of equipment which has been specifically designed to supply large quantities of electricity for any required application. We are not dealing with the spare capacity of some low-grade alternator in a car, but we have substantial electrical power available. Having said that, the electrolyzers described at the start of this document are efficient, and it is unlikely that an excessive amount of power would be needed when using one of those designs. Another convenient factor is that this is a stationary application, so the size and weight of the electrolyzer is not at all important, and this gives us further flexibility in our choices of dimensions. As this is an application where it is highly likely that the electrolyzer will be operated for long periods unattended, an automated water supply system should be provided. The main details of such a system have already been covered, but what has not yet been dealt with is the switching for the water pump. The water pump itself can be an ordinary windscreen washer pump, and we need some form of switch which operates on the electrolyte level inside the electrolyzer. It is sufficient to sense the level in just one of the cells inside the electrolyzer, as the water usage will be pretty much the same in every cell. If you make the electrolyzer in a suitable size or shape, then a simple off-the-shelf miniature float switch can be used. If you prefer, an electronic level sensor can be operated, using 2 bolts through the side of the electrolyzer as the level sensor. A suitable circuit for this simple switching task could be: when the electrolyte level inside the electrolyzer is in contact with the upper bolt head, the circuit is switched off and the water pump is powered down. The electrolyte has a low resistance to current flow, and so it connects the 4.7 kilo-ohm resistor through to the base of the BC109 Darlington pair, as described in Chapter 12. This keeps the 2 transistors switched fully on, which keeps the 8.2 kilo-ohm resistor connection well below the 0.7 volts needed to switch the ZTX6533 transistor on. If you are concerned about the ZTX6533 transistor being partially on, then resistor R could be added, although the prototype did not need one. The value would be about 2 kilo-ohm. When the electrolyte level falls below the upper bolt head, the first 2 transistors switch off, and the ZTX6533 transistor is then powered fully on by the 4.7 kilo-ohm resistor and the 8.2 kilo-ohm resistor in series, providing the 150 milliamps needed for the relay to be switched fully on. The circuit draws about 5 milliamps in its standby state. The numbers on the relay symbol correspond to the numbers on a typical automotive 12-volt relay. Using 2 BC109 transistors as the front end allows the circuit to be used with tap water if you wish. However, the water level control for the water supply to the pond fogger or Venturi tube misting device does not need any form of fancy mechanism. The standard ball-cock valve mechanism which is used with toilets is quite adequate, especially if a floating pond fogger is being used, as it maintains its own optimum depth below the surface, and so the overall depth is not in any way critical, provided, of course, there is sufficient depth for the fogger to float correctly. Starting. When left for any length of time, the gas pressure inside the electrolyzer will drop because the nature of the HHO gas alters. This means that there will not be sufficient HHO gas available to start the engine, and no more gas will be generated until the engine drives the generator. So, to deal with this situation, a lead-acid car battery is included so that it can be switched in to replace the generator for a brief period before the engine is started. That inclusion gives this overall arrangement. This arrangement is perfectly capable of running a standard generator without the use of any fossil fuel. It should be noted that while no fossil fuel needs to be bought to run this generator system, the electrical output is far from free and is actually quite expensive, as there is the purchase cost of the generator, the electrolyzer, and the minor additional equipment. Also, generators have a definite working life and so will need to be refurbished or replaced. It might also be remarked that if a generator of this type is going to be used in an urban environment, then the addition of sound-reducing baffles and housing would be very desirable. At this point in time I am aware of 9 different electric generators which have been adapted to run on water. At least 4 of these are from different manufacturers. The method of altering the timing and dealing with the waste spark is different from one adaptation to the next. One user has altered the spark timing of his generator to after top dead center by rotating the timing disc to a position not envisaged by the manufacturer. The timing disc is held in place by a locking key bar, which fits into a channel cut in the shaft of the engine, matching it to a similar channel cut in the disc. The alteration was achieved by cutting a new channel in the shaft, allowing the timing disc to be positioned further around the shaft, producing the required timing delay. This arrangement also makes the waste spark ineffective and so it can be ignored. While this method requires the cutting of a slot, it does away with the need for any electronics, and it is a very simple solution. If you feel that the construction of a suitable electrolyzer would be a problem, or that the amount of electric current needed to operate it would be excessive, let me show you the actual figures involved. Michael Faraday was an exceptional and highly respected researcher who investigated the electric current needed to convert water into hydrogen gas and oxygen gas by electrolysis. His results are accepted by pretty much every scientist everywhere. While he expressed the results of his work in terms which would be meaningless to the average person, his result is that an electrical input of 2.34 watts produces 1 liter of HHO gas in 1 hour. In practical terms, that means that a current of 0.195 amps at 12 volts will produce 1 liter of HHO gas in 1 hour. In passing, only a nearly discharged lead-acid battery would have a voltage of 12 volts, as the fully charged state is 12.85 volts, and a vehicle alternator produces about 14 volts in order to charge the battery. It is easier then to compare the gas output of electrolyzers directly to the figures produced by Faraday as shown here, based on a gas output of 15 liters per minute, which is 900 liters per hour. Faraday, 900 liters in 1 hour, takes 2106 watts or 100% Faraday. Boyce, 900 liters in 1 hour, takes 998 watts or 211% Faraday without pulsing. Boyce, 900 liters in 1 hour, takes 180 watts or 1170% Faraday with pulsing. Crampton, 900 liters in 1 hour, takes 90 watts or 2340% Faraday. Much of this is not very important, as it has been demonstrated that a gas production rate of around 3 liters per minute, 180 liters per hour, is sufficient to run a generator which produces 5,500 watts. Let us assume that the measured figure is 100% wrong and that it takes 360 liters per hour of HHO gas, plus cold water fog, plus air, to run the generator. Then Faraday would need 843 watts. Boyce would need 400 watts without pulsing. Boyce would need 72 watts with pulsing. Crampton would need 36 watts. None of these figures are important for running a generator, because with an electrolyzer efficiency of only 50%, Faraday still leaves a massive generator excess of nearly 4 kilowatts on a 5.5 kilowatt generator. The gain is in running a generator as an internal combustion steam engine and not in the great efficiency of the electrolyzer. It is distinctly possible that the pessimistic figures shown above are twice what is actually needed, but who cares? The facts speak for themselves, with several people scattered around the world, already running generators on water. Many different generator designs have been adapted, typically, by modifying the flywheel, filling in the keyway and cutting another one to give a spark 2 degrees after top dead center. Experience has shown that the 6.6 kV Honda V-twin petrol motor generator and the Vanguard V-twin work very well long-term when adapted to run on water only. Wear and tear issues. A man who lives in Alaska is very experienced in the use of renewable energy sources and unconventional fuel systems. His experiences are likely to be helpful for anyone who intends to use an electrical generator, whether running on water or on a fossil fuel. He recalls the experiences of a friend. He decided to live off the grid because it was going to cost him $20,000 to get connected to the grid, and as his house was not that large, he decided to go the alternative route. We designed a system which would use a 4 kilowatt inverter and have an 8 kilowatt Briggs & Stratton generator with a 13 kilowatt surge capacity, for backup. The system has 6 solar panels and a 24-volt battery bank with 400 amp capacity. Having long summer days here in Alaska, the solar panels have more than enough capacity for charging the battery bank on sunny days. However, but when the day is overcast or when it is winter, when there are only 6 hours of sunlight, the battery bank does not get charged fully. At these times, the generator is used to top up the battery bank. American generators normally have either 2 or 4 120-volt outputs each rated at 15 amps, plus one 240-volt output rated at 33 amps. If one of the two 120-volt outputs is used to charge the battery bank, then you get left with just the other 120-volt output for any other power needs during the time when the battery bank is being charged. This is not a satisfactory arrangement, as operating with one field at maximum power and the other one lightly loaded or unused, causes a field imbalance in the generator, engine crank imbalance and ring or regulator failure within 6 months. It also causes noisy running and excessive fuel consumption. Run in this way, providing a 60 amp charge rate, the generator ran hard and loud for 2 to 2.5 hours per day, and running it was costing $350 per month for gasoline. The generator failed after 4 months. In order to balance the loading on the replacement generator, a 15 kV step-down transformer costing less than $1,000 was purchased so that the 240-volt output could be used to drive 120-volt equipment. A transformer to be used for this needs to have a power handling capacity which is greater than the surge capacity of the generator. A major advantage is that the generator current is halved for any given level of equipment current drawn because the equipment is running at only half of the generator voltage. Using this transformer made a massive difference, giving a balanced output and providing a 90 amp charging rate for the battery bank, as well as having ample power to run other household equipment when the battery bank was being charged. The result was a charge time of just 1 hour 20 minutes per day, with the generator running quietly and smoothly. The fuel consumption also dropped to just $70 per month, which is just 1/5 of what it was, covering the cost of the transformer in under 4 months. This generator has been running now for 2 years without any problems at all. The step-by-step conversion of a generator. Selwyn Harris of Australia has kindly agreed to share detailed information on how he performs the conversion of a standard electrical generator to enable it to run on water alone. The generator which he uses as an example for this tutorial is a GX4000i generator. The supplier is AGR Machinery, which is an Australian company on eBay which buys up stock from collapsed companies and resells the equipment. The supplier says, GX4000i portable type generators have smoother output power, comparable to public utility sources. Ideal for powering medium loads such as power tools, both single and 3-phase, game consoles, digital cameras, laptops, camcorders, lighting and microwave ovens, drills, grinders, resistive load kitchen appliances, that is, coffee maker, toaster. Emergency home backup power where 240-volt power is required. Also, these units are significantly quieter than others due to refined engine technology. Features: commercial grade engine, 196 cubic centimeter 4-stroke, 7 horsepower, overhead camshaft, TDI ignition. Maximum output 4.0 kV ampere at 240 or 415 volts AC, rated output, 2.7 kilowatts. Quality heavy-duty construction. AVR, auto voltage regulator. 3 240 volts and 1 415 volts protected outlets. 100% pure copper core. Gearless direct drive. Robust square frame design. Easy recoil start. Oil capacity, 0.7 liters. Powder coated finish. Light and compact for easy maneuverability, 38.5 kilograms. Noise level, 69 decibels. The first step of the conversion is to remove the fuel tank, which is held in place with 4 bolts. This allows access to the carburetor, which is then removed as it will not be used. The next step is to construct a pressure release valve mechanism which will protect the equipment from damage in the unlikely event of a major, sudden rise in pressure caused by the unwanted ignition of the HHO gas mix used to power the generator. For this, parts are purchased from the local hardware store. The brass fittings are a 12 mm barrel, a 12 mm female T-fitting and a 12 mm to 9 mm hose reducer as shown here. The polyvinyl chloride plastic fittings are a 1/2 to 3/4 reducer and a 3/4 end cap, along with the roller ball from an old-fashioned mouse and a relatively weak compression spring to hold the ball in place during normal operation where the gas pressure is low. These components are then assembled to produce the pressure release valve. The inside of the flash arrestor looks like this. Drilled vent holes. Polyvinyl chloride cap. Weak spring. Roller ball. Female thread brass T-piece. The ball is held in place by the spring allowing the HHO to flow past it, but if a sudden increase in pressure should occur, then the ball is forced upwards, opening a path to the many holes drilled in the plastic fittings. When the gas pressure drops again, the spring pushes the roller ball down to seal off the pressure release holes. However, Selwyn adds an additional spring-loaded valve to the arrangement. This one is there in case the electrolyzer fails to produce a sufficient volume of gas in the event of a sudden increase in demand. This valve is marked as a vacuum relief valve, although, strictly speaking, it deals with reduced pressure rather than an actual vacuum. The arrangement is shown below. Please take note of the fact that Selwyn uses the Hog style of electrolyzer and that design has a bubbler built into it, so if you are using some other design of electrolyzer, please be very sure to use at least one bubbler between the electrolyzer and the engine, in spite of the fact that there is very little chance of the engine misfiring and igniting the HHO gas in the electrolyzer. For an engine of this size, an electrolyzer which produces 4.5 or 5 liters per minute of HHO should be adequate. The addition of cold water mist through a Venturi tube as shown, both lowers the engine temperature and increases the engine power as the mist converts instantly to flash steam when the HHO gas ignites, raising the pressure inside the cylinder and boosting the power output. Next, a piece of 6 mm thick aluminium plate is cut and shaped to the size of the carburetor gasket, which is not a symmetrical item. This is done by tracing the gasket and transferring it onto the aluminium plate, drilling the holes and then cutting out the outlined shape. The edges are then filed to create a nice fit on the engine port. The pipes, backing plate, pressure relief, vacuum relief, gaskets, nuts and bolts are then assembled as shown above. Most of the pressure relief valve components shown in the photograph have been painted, which happens to conceal the different materials being used. At this point, an electrolyzer of any design which can produce at least 4.5 liters of HHO gas mix per minute is connected to the intake. The electrolyzer most often used by Selwyn is the Hog design disclosed by him earlier in this chapter. The manual pull start and the generator cover are now removed. It is only necessary to remove 4 of the bolts to take the cover off. This is the engine with the starter pull and the blower cover removed. At A you can see the magnetic pulse type transistor discharge ignition pickup in its original position, bolted in place at 8 degrees before top dead center. This needs to be removed and an aluminium plate inserted to allow the transistor discharge ignition to be mounted in its new position. Because of the new fuel, it is necessary to retard the ignition system. This can be done in one of 2 ways, neither of which is particularly easy, so you may need the help of an engineering shop. The easiest way is to modify the installed ignition to top dead center. This is Selwyn's aluminium transistor discharge ignition adapter plate, which he made from 2 mm thick aluminium sheet. In this picture, the outline of the fuel intake port is obscured due to it having been temporarily blocked off during the construction. The tools required for constructing these components are a drill press and a jigsaw fitted with a metal blade. Selwyn used this timing alteration method on his own smaller generator, which has run trouble-free for a year. The objective is to delay the ignition spark from 8 degrees before top dead center to either top dead center or to 1 degree after top dead center. This allows for a good spark on the compression stroke, and when the waste spark occurs, the inlet valve has not yet opened and so there is no HHO is in the ignition area. That is to say, the exhaust valve has just closed and the inlet valve has not yet opened. This results in a good compression stroke for the HHO and does not try to send the piston backwards due to premature ignition of the gas mix. The above picture shows the aluminium plate mounted and ready to accept the pickup. This plate needs to have air holes drilled in it in order to allow cooling air to flow over the engine fins behind it. The transistor discharge ignition adapter plate looks like this. And as shown below, the support plate is drilled with the ventilation holes. In this photograph, the adapter plate is just resting on the support plate. Later, when the top dead center timing position is established, the adapter plate will be bolted to it using the 3 holes top and bottom on the white plate. This locks the timing to that setting and the timing is never changed. In 2010, when adapting a previous generator, an experienced mechanic was asked to establish the transistor discharge ignition plate position and he charged $60 for doing that. Finally, the covers and the starter handle need to be bolted back in place. Instead of paying somebody else to set the new spark timing, it is perfectly possible to do that yourself. One effective method is as follows. Mark the casing of the engine in a convenient location as shown in yellow in this photograph. Remove the spark plug and insert a long screwdriver until the top of the piston is felt. Manually rotate the engine, clockwise for this generator as can be seen from the curved fan pieces on the flywheel, until the screwdriver is no longer pushed upwards. It may take more than one rotation to find this point accurately. When that point is found, mark the flywheel directly in line with the casing mark which you just made. This marking needs to be very accurate. Continue rotating the flywheel very slowly until the screwdriver starts to go down again and mark that point on the flywheel. Again, this marking needs to be very accurate. Measure the distance along the flywheel between the 2 flywheel marks which you have just made and then make a larger mark on the flywheel exactly halfway between your 2 marks. If accurately done, this new point is where the flywheel is when the piston is exactly at top dead center, which is where we want the spark to occur. This marking on Selwyn's flywheel is like this. Next comes a bit of arithmetic. The diameter of the flywheel is 180 mm, which means that its circumference is 3.14159 multiplied by 180 equals 565.5 mm, and as there are 360 degrees in each rotation of the flywheel, then the outside edge of the flywheel will move 1.57 mm for each of those degrees. The engine specification states that the spark timing is 8 degrees before top dead center and we want the spark to occur exactly at top dead center, which means that we want 8 multiplied by 1.57 equals 12.5 mm of the flywheel circumference to have passed by before the spark occurs. To achieve this delay in the spark timing, the transistor discharge ignition needs to be moved 12.5 mm in the direction which the flywheel rotates. You will notice that for this major timing change, the transistor discharge ignition adjustment is very small, only half an inch. When the transistor discharge ignition adjustment has been made, the timing can be checked using an automotive timing light connected to the spark plug lead. The engine can be spun using an electric drill. As the flywheel is spinning fast and the flash of light from the timing light is very short, it makes the flywheel mark appear to be stationary in spite of the fact that it is passing by very rapidly. If the transistor discharge ignition adjustment is correct, then the central mark made on the flywheel will appear to be stationary and exactly aligned with the mark made on the casing. This is exactly what happened when Selwyn's motor had its timing adjusted, but the important factor is to have the spark close to the top dead center point to make sure that the inlet valve is fully closed before the spark occurs. 2 degrees after top dead center is a popular point for the spark with many of the existing generator conversions which I have been told about, possibly to reduce the loading on the piston's connecting rod. Here is a photograph of Selwyn's latest generator conversion having its new spark timing checked out. Most small petrol engines have the spark timing set between 8 degrees and 10 degrees before top dead center. If it so happens that you do not know what the timing of your particular generator is, then complete the flywheel marking procedure of step 4 above, but make 3 additional marks on each side of the top dead center mark. Space those marks 1.5 mm apart as they will then make a scale which shows each degree from 3 degrees before top dead center to 3 degrees after top dead center. When the timing light is used, It then shows exactly where the spark occurs, and if the engine had an original spark timing which was not 8 degrees before top dead center, then the scale shows immediately how much further the transistor discharge ignition needs to be moved to set the spark exactly where you want it to occur. The cold water mist. Getting the fine droplets of water into the engine can be done two different ways. The first way is to use a Venturi tube which generates a fine spray of droplets when air moves rapidly past a small water-filled hole. You may not have noticed, but this method has been used extensively in perfume sprays and it is very effective. Selwyn describes how he constructs a Venturi tube. A short length of 1/4 inch, 5 or 6 mm, diameter copper tubing is used. This is generally available as central heating supplies, and if there is any difficulty in finding some, then your local garage can probably direct you to a supplier, if they don't just give you a short length from their own supply. The copper pipe is then heated with a plumber's gas torch and bent very slowly and carefully to the shape shown above. Some people find it helpful to insert a length of suitable flexible material into the pipe before starting the bending, something like the coiled steel spring material used to support net curtains, as that helps to keep the copper pipe from kinking when being bent. Next, the end of the copper pipe, which will form the nozzle, is filled with silver solder and the end filed flat. Then, a small hole is drilled through that silver solder plug. The smallest possible drill bit should be used for this, although the hole may need to be drilled out to a slightly larger diameter, depending on what the engine requires, which is found by successive trials. This Venturi tube is to be inserted into the last brass fitting before the engine, so a 1/4 hole is drilled through the brass and then the drill is removed very slowly at a slight angle, the angle of drag being down the axis length of the brass fitting. The copper Venturi tube is then inserted through the hole and positioned so that the Venturi hole is aligned up exactly with the centerline of the brass fitting and positioned exactly in the middle of the cross section of the brass fitting and then soldered in place. The method which Selwyn uses to block off the end of the copper tube with silver solder is to seal the far end of the tube with tape and fill the tube with fine-grained sand like this. And then the tube is heated with the gas torch flame and the solder run into the top part of the tube. When the solder has cooled, the tape is removed and the sand removed by tapping the tube. When the hole has been drilled through the solder, air is blown through it to dislodge any remaining sand, and then water is forced through the hole. As the tube is short, any remaining sand can be removed with a pipe cleaner or any similar slender cleaning device. The installed Venturi tube can be seen here. The second way to introduce cold water mist into the airstream entering the engine is to use a commercial pond fogger which can be bought at pet supplies outlets. These have to be powered electrically and housed in their own water container. Some of the more advanced versions float on the surface of the water so that the fog generating section is always submerged to the ideal operational depth below the surface of the water. The generator should run well with 5 liters per minute of HHO gas plus cold water mist. Any design of electrolyzer can be used. However, when used with rainwater, the Hog electrolyzer will draw about 1.4 amps per cell, giving a total input of about 115 watts when run on a 12-volt electrical supply. While rainwater is supposedly pure, the reality is that it seldom is, and its ability to carry a current varies dramatically from place to place and even more widely from country to country. However, regarding the water, Selwyn says, "The water I use is treated in a special way to make sure that the electrolyzer runs at the lowest temperature and amperage possible. For this, using rainwater is a must, and the rainwater coming off a steel roof is the best. The water is then treated by inserting a double coil of stainless steel wire into a volume of about 5 liters of water. A supply of 12 volts DC is applied to the coils, and the resulting current allowed to run through the coils for about 5 hours. This results in hot and very dirty water. The water is then filtered using a 0.5 micron filter, making the water ready for use in the electrolyzer. If more water is needed, say 30 liters, then leave the coils running for at least 24 hours. I use an old 35-liter beer keg and prepare 30 liters at a time. A major reason for doing this is to remove all the solids suspended in the water so that they will not clog up the stainless steel mesh inside the electrolyzer. After the construction of the Hog electrolyzer is completed, then the stainless steel mesh electrodes need to be treated and cleaned. For this I use distilled water and fill the electrolyzer enough to cover all the plates, and then add 1 packet of citric acid for each 3 liters of water used to fill the electrolyzer. I got the citric acid from www.hhoresearch.com.au, which is an Australia-only supplier, and each packet has about 22 grams of citric acid in it. The pumps are then run for about an hour, after which the Hog tubes are washed out completely with distilled water and then allowed to dry completely. This removes any residue from the stainless steel mesh electrodes, making the gas production rate much greater. I use an ordinary car battery to generate the HHO gas needed to start the generator running, after which, a standard battery charger powered by the generator output is used to keep the starting battery topped up. There are YouTube videos which show generators being operated on what appears to be just HHO gas alone, and while the operation does not appear to be anywhere close to full power, the addition of cold water mist would probably make a major difference to the performance, but it does demonstrate that a generator can certainly be run without using any fossil fuel. The spark circuit in the first video appears to be powered by a small mains unit. But as the generator is lighting a powerful lamp, that electrical input could almost certainly be met by the output from the generator when it is running.